you all, friends and colleagues. My name is Fredrik. I'm one of the founders of Mullvad VPN, among other things. My colleagues Sasko and MC are two of the ones who've been working together with me and others on what we're going to spend most of this presentation talking about. And in short, at Mullvad, we have a systematic focus on trustworthiness, transparency, and trailblazing. They are our internal cultural pillars, so to speak. And we've decided to spin off a few of our research projects as separate companies. Two companies. One is Glasklar Teknik, that means crystal clear technology, and it will focus on our transparency log design SIGSUM, which gives transparency to signed checksums, and system transparency, which is a security architecture for making running systems transparent. And the other one is called Tillitis, which is a play on words from the Swedish word tillit, which means trust. And we've made a piece of hardware. This one. You have it in your goodie bags. One moment. Yeah, it's basically the answer to the question, what if system transparency made hardware instead of designed a software security architecture? Consider that this is a greenfield design. So we tried to take a first principles approach and look broadly across different platform security technologies. Yeah, this is what we came up with. So one of the early ideas we had was, okay, let's make a tiny trust anchor. So let's do a minimal as minimal of an ED25519 signer as possible. This is the wrong presentation. Oh my God. Oh, you downloaded it yesterday. Yes. Oh no. Sorry. Well, so the thing is, everything basically came down to the wire. Literally, we thought we had issues with the UART last week, and in the end, we were like, the signatures are wrong because the multiplier isn't working. And by multiplier, I mean we have a Pico RV32 inside of the DICE 40 Ultra Plus 5K FPGA, and the multiplier instructions weren't returning the right values, and that is why we couldn't get valid ED25519 signatures. Oh no. Okay, I'm very sorry. In any case, the first thing we did was we designed so we took a PMOD module. We took the ICE 40 Ultra Plus 5K FPGA, and we made a PMOD module out of it with an FPGA design that contains the Pico RV32 32-bit RISC-V CPU soft core, and we put ED25519 signing software in there. And so we basically had this tiny little, it's the size of a €2 coin, and I have a picture I'll show you later. And that it's just a signing oracle. So it's the tiniest implementation we could do, or the smallest way that we could express the essential complexity of, here's a message, please give me a valid ED255 signature on this message. Yeah, so then we iterated on that, and eventually is it up? Nice, thanks. All right, so now hopefully I can show you. Thank you. Thanks. All right, so here it is. Matt Metz of Blinking Labs is in the audience. He helped us with the physical design and manufacturing of all of our hardwares. Here you can see the MTA1 signer, Mullvad Trust Anchor 1, and that's what you have on your PCB as well. That's because we manufactured it before. We decided, you know what, let's make this into a separate company. And yeah, so here it is. And let me see. It's the first one we made. And then the next slide should be our colleague. Yeah, so that's our colleague Cookie. And he's placing, as you can see, he's picking and placing components. For some reason, he's decided to forego the solder paste. And if you're really paying attention, what I can see here is actually, if you look in the up left corner, he's made a mistake. See? That's not the right, whatever that is. Okay, sorry. Yeah. Anyway, so here's the physical result. And yeah, it's pretty small. So anyway, now I'm going to talk about the Tillitis key. Warning, these are engineering samples. They will not burn up, but there are plenty of things that we haven't dug into yet. We have done a considerable amount of work on understanding the lattice size 5K, or rather, Trammell Hudson, together with Matt, has collaborated with us and been immensely helpful in, well, we've learned way more about the FPGA than we, well, I guess not than we wanted to, because we wanted to. But there are tons of hilarious and interesting things to say about the boot state machine and EBRs that won't, reset on warm reboot and so on. But we can talk about it afterwards. But what I was going to say is specifically the firmware in the microcontroller that we have in front here that implements USB. We haven't audited that yet. So if there's an RC in there, an attacker can get persistence from the host. They can't update the firmware because the USB host controller won't be able to do the port knocking with the microcontroller from the host side. But so it's still a prototype. In any case, this is what it does. Let me see. 1 second. All right. This is what we came up with. So it does unconditional measurement and key derivation. The key derivation function is, if I remember right now, we're using Blake 2S. There's a unique per device secret inside of our FPGA design. It's read once per reset, so it can only be read by the ROM on die firmware. The ROM on die in this case being the machine instructions that are in the EBR part of the FPGA. Then it hashes the first mutable boot stage, which we serve up from the host. And then we also hash in optionally a user-supplied secret. And so this then becomes the secret that we hand off to the first mutable boot stage, which means every single app that you load onto the stick gets its own secret. Yeah, it turns out to be immensely useful. I, at this point, I would also like to express my personal gratitude both for Joachim Strömbergsson, one of my colleagues who is over there, who taught me tons of things about FPGAs and how hardware works over many years. And eventually, yeah, we started building this. And Trammell Hudson, who has been a fantastic sounding board, and we yeah, have a nice design feedback loop. But in any case, yeah, this is the end result so far. And yeah, I think this is one of the things I usually say. As systems become more complex, we have to manage the complexity better. If we don't, then we'll end up with complicated, incomprehensible, and ambiguous designs, which increase doubt and so on. But if we instead make design simple and understandable and so on, then it becomes easier to trust them. It's probably obvious, but we should make things obvious, because then we have confidence in the provided security. This is a quote I really like. So the thing is that hardware, it defines software itself through its physical design. Software is sort of an emergent phenomenon in the electricity on top of the hardware. That's one way to think about it. But it is immutable, and of course it's not always designed correctly, and there are bugs in it. But nevertheless, it's hard for a digital attacker to affect the to gain persistence in the hardware, because it's laser painted Boolean logic on sand, and the digital attacker won't be able to change that. And so I would argue that these are the two things that we can be most certain about. One is hardware, the other one is cryptography, because modern cryptography relies on computational hardness. It relies on this particular math problem is easy to do one way and it's hard to do the other way. So if we can combine these two, we have two fantastic levers that can make things hopefully both easy to understand and also really hard to break. Modulo glitching and differential power analysis and other physical attacks. Here's another way to think about it. That we have the hardware that then defines the possible state space for the next stage, and which is firmware, which in turn defines the possible state space for the OS kernel, and so on and so forth. Because of course, yes, computers are Turing machines, but the tape is not infinite, right? It's just a few gigabytes of RAM. So it is, in one sense of the word, a state machine. And if we can confine every, using CPU modes like supervisor mode and user mode, we can confine the possible state space until we end up with a virtual machine for JavaScript, and hopefully that one can't escape out of there. And so then cryptography as a field, they strive to remove or reduce assumptions. For instance, in elliptic curve cryptography, you have the issue of nonce reuse. So then ED25519 came along and said, let's just put SHA-512 in there and use the hash of the message as the nonce. And boom, that's more robust. Same thing with MD5. If we put MD5 in an HMAC construction, or then HMAC MD5 in a HKDF construction, that also reduces the assumptions on the underlying hash function. So yeah, in the end, we came up with this. It's based on DICE. Microsoft got a lot of things right about DICE. I encourage you to read the spec. And in essence, the idea is, let's have an integrity-protected first boot stage, ideally in ROM on die. What should it do? Well, it should do one thing. It should measure the second boot stage, the first one that is mutable, wherever it comes from, whether it's on your SPI flash or from the network or elsewhere. And then based on the digital fingerprint, the hash value of this first mutable, the first mutable boot stage, that should change the platform identity and its ability to authenticate. I detail that. I should mention here is that in in ED25519, for instance, most of the 32-byte values are valid secret keys. So you can use any value to create a ED25519 key pair, and thus use that as the identity. So you have an identity that is based on the unique per device secret, which is unique per chip. And how to create that is another topic. And then you mix that in with the first mutable boot stage. And so that is the identity of the system. And you can carry that forward if you continue the unbroken chain of load, hash, measure, execute, that cycle. Yeah, and I think this is also a topic for another talk, but I would argue that there's a group of engineers that we could, that I think hardware, firmware engineers could learn a great deal from, and that is the group of engineers that has already for many years applied the combination, so researched and studied the overlap, the combination of state machines and cryptography. And that is secure communication protocol designers. They take cryptographic constructions in primitives and make constructions of them that are, TLS 2.0, pretty terrible. Same thing with RPSec. TLS 1.3, and I mean SSL 2.0. WireGuard, TLS 1.3. The connections between the primitives are rock solid, and it's going to look differently if we use the combo of ideas about state machines and cryptography for platform security. But nevertheless, I think that we can take a great deal of inspiration from them, and I think maybe that's how Microsoft came up with DICE. Yeah, that's cool.
You hear me? Okay. Sorry for messing up, so I will have to make up some of the time. What I will go through is the Tillitis key, and after me, MC will show a demo of what it does and as of today. So this is an open source hardware and software device, and I will go through the hardware and show how it works theoretically. So first, hardware first. 4-layer stack up, 27.5 by 13.5 millimeters in dimension. On the bottom side, we have 20 test points, which you can use to measure different levels, voltage levels and signals. And we also have a programming interface, which I will come back to later. On the top side, we have all the components. And basically, it is what Fredrik showed before. So we have the ICE40 FPGA. We have the CH552 MCU for USB to UART protocol conversion. The SPI flash for configuring the FPGA. We have the touchpad area for asserting physical presence. And 2 LEDs. Inside the FPGA, we have a RISC-V Pico RV32, which runs the whole show. We have a ROM for the firmware, RAM, a touch block, which interfaces the touchpad. We have the UDS, UART timer, true random number generator, and what we call MTA1 block, which is interfacing all the LEDs, or the 2 LEDs and the GPIOs. So, 2 things. What happens when the key is used and how to update the FPGA, the firmware, or the UDS. So first, you have the hardware. So I'm trying to picture here a logical stack of how the key actually looks. And we have the most important part is the FPGA and the touchpad SPI flash. So you plug it into a computer. It powers up, and the SPI flash configures the FPGA with all the components inside, all the blocks. In parallel, the firmware on the CH552 starts, and the key is ready for use. So what you need now is some kind of program or application on the host side that knows how to use the key. And inside that host application, we have the device application. So the first thing that happens is that the device application is uploaded to the key. And then the magic happens, so to say, where the firmware hashes the device application and then measures. And after that, it jumps to the device application. and it starts to execute the application. In practice, it can be something like this then, that the host application is the SSH agent, and the device application is the ED25519 signer. And this is actually what the demo will be about. So if you want to modify the FPGA design, firmware, or change the UDS, you'll need a programmer. And this is something you have in the box as well. And the programmer uses the programming interface at the bottom, as I described before, to program the SPI flash. The programmer itself is a board with a Raspberry Pi Pico board and a socket for holding the USB. So you have to open up the casing and place the USB in the holder, close the lid, and via the micro USB on the left side there, connect to the computer and program. And that's how you update the firmware, the FPGA design, or change the UDS. Pretty fast, but I hope it was clear. So, MC, demo.
Okay, let's see if this works. Can you see anything? Is it large enough? Right, let's see then. So what I'm going to show is using the stick as a signer and your identification when you're using SSH to log into some place. And at first you start by inserting the stick in your computer. Then you start our version of the SSH agent. Something like this. But let's be sure that the socket isn't there first. So you pass the socket to the agent, so the SSH command can find this agent. So let's start it. And it's connecting to the device, and it's loading the app. It's currently a bit slow because of hardware reasons. And we will probably update that in a later design. And now it's loaded the signer app into the device, and you can see that we asked it about the public key. And this is the public key. So now you somehow transport this public key to your the machine, the target host. And this is done magically. So now I have the public key in my authorized key on the target host, which means I can log in with the corresponding private key, which is in the stick. So using this command, this is an SSH command with an environment set to the socket. And I'm trying to SSH into localhost. And somehow, it said I had to touch the device because this is a signing request that has come through the SSH agent to the USB stick, and the USB stick is now flashing green and waiting for me to touch it. So now I'm touching it. Let's see if the demo gods is with me. And I'm in. Yeah. So if I log out and do this again, it will be slightly same thing again, and I'm in. So yes, this is how it works, and this is immediately useful for everyone who has ever used SSH. You can use the stick as your private key, and this has a number of conveniences. Instead of having your private key in your home directory, even if it's encrypted. For development purposes, we also have, if you don't have a key, in your goodie bag there's a key, but if you don't have a key, if you're watching this in a stream somewhere, or you want to develop on this thing right now, we also have an emulator. We have a fork of QEMU, and with support for most of the stuff in the stick. So you can run the exact same thing without the real hardware on the emulator. And then we are also releasing the apps themselves, so you can use those apps as the beginning of your own app. For instance, this is a simple elliptic curve signer right now, but if you don't want to use that, you can write your own app and make it do whatever. And there's also a development tool called Run App in the same repo. Instead of using the SSH agent, you can use Run App, which loads the app and then tries to speak to it, and you can use that as a base for your own software. And let's see. Yeah, I think that was it. So over to the Sasko again.
Well, basically it's to round up and start the Q&A. So in summary, you have seen the Tillitis key, which is a USB security key inspired by Measured Boot and DICE. It's open source hardware and software. You have an engineering sample and a programmer in the goodie bag. Instructions can be found on tillitis.se or come by our table in the hackathon room. MC Joachim, we'll be there most of the time during breaks. So, thanks.
All right. I just want to clarify two things before we begin the Q&A. So the programmer that you have should be able to program and lock the on-die, or sorry, in-package NVCM memory. And you can do that with open source tooling thanks to Matt and Trammell, who reverse engineered the format. So you can now program and lock the ICE40 up5K thanks to them. The engineering sample that you have, as Sasko mentioned, contains the bit stream for the FPGA design, as well as, and obviously, the ROM on die in that bit stream with the firmware. And because the UDS is part of the UDS core is part of the bit stream, the UDS is in there too, in the SPI flash. So a physical attacker that wants to extract your UDS from the stick you've dropped on the ground can do so with the conveniently provided programmer. So just so you're aware of that. And let's see. Yeah, and the unfortunately, I didn't have time to update the threat model online. So it's an engineering sample, and don't use it for the crown jewels right now. Yeah. All right.
Thank you. All right, thanks, first of all. And I see a couple of questions. I think Daniel had a question and a couple of ones over there. So Max will come over and give you the mic so that you can.
Yeah, we have Joachim here as well.
Oh, nice. Yes, great. Yeah, so this is Joachim Stromberg, who, he's the cryptography and hardware FPGA design expert.
Yeah, thanks. Cool stuff. I actually just got started with FPGAs and bought 2 of the orange crab boards, and now I have a third IS40. Thank you. So, being an application developer, so when I now want to write my application for this, I essentially just write an RV32 bare metal application targeting the Pico RV2, right? And then I can just run it. Are there any like specific APIs or some sort of SDK that I can use, or?
It's basically just Clang. You can check out our example apps and use that as a start for your own app. And we provide a couple of extra functions for I/O and stuff like that, and you can use them to speak to the host software, for instance. But other than that, yes, you're right. That's a simple RISC-V 32, and you can use whatever tools you want. If you want to write things in Rust or Zig or whatever, you can probably do that.
Yeah, Rust sounds about right. So we're gonna generate some SVG files, I guess, and then derive the crates. And thank you.
So yeah, cool demo. I'm wondering if it's if my guess is correct that the output of the KDF of UDS, USS, and app measurements is used to deterministically produce the signing key that was used. And if so, I'm also wondering, like, if does this design contemplate a future in which we also turn that into like an alias key so the app can prove its own measurements to someone else, like a remote verifier?
So are you asking if our plan is to have some type of remote attestation mechanism?
Well, that's one of the use cases of DICE, right? It's like you make an alias key, so now it can sign things, and the certificate has its measurements.
Yeah, is that what you're asking?
That's what, yeah.
All right, yeah. So you can chain load applications, and the mechanism for that is something will probably change. But the idea is that, so for instance, what you could do is you could your first mutable boot stage could be a tiny loader that simply, it contains a trust policy that does verified boot of the next stage. So you upload the first stage, and it will verify code signing signature on the next stage. And because at that point your TCB is the first mutable boot stage, which got its identity based on its hash value and the UDS, you can then hand off that thing to the next stage. So you can do, for instance, let's say you want to develop your own 825519 signer app, but you want the key pair to persist across software updates. Then you would have the loader containing your public key as the developer, and as long as you don't update the loader, the key pair is the same, and you can update the second stage. Does that make sense?
So the FPGA bitstream wouldn't be responsible for like being the root of the DICE attestation hierarchy. That'd be the first mutable code then.
Yeah. So what the idea is that you can have every stage produce a certificate-like data structure that contains, let's say, the key pair for the next stage and the hash value for the app of the next stage, and then you sign that whole thing with the first secret, and then when you hand off to the next stage, eventually you get like a PKI that says, this is such and such a Sage app signed by this. But no, there is no, the hardware doesn't, there's no root certificate in the hardware that, yeah.
Makes sense, thank you.
Yeah.
Hi, I'm Joey. First of all, really cool that there's another Swedish security key company. And that was my question was, does your research indicate that people are interested in an open source firmware solution for security keys? Or, I mean, because Yubico is such a large portion of the market, how do you think you all stack up against them? Or is it not even a fair comparison to make?
Great question. Okay, can I? Yeah. Okay. So the thing is, as I mentioned at the start of the talk, internally at Mullvad, we are obsessed with making our systems more trustworthy, transparent, and and so on, and we want to spearhead that. So when we started, there was no consideration taken into, oh, does the market want this? It's that's usually how things happen. It was rather, if we wanted, if we could. We had a few research questions, and they were like, how can we? One was, how can we express the essential complexity of an ED25519 signing oracle if we make it as open source hardware and software as possible? Another question was, what is the how should a platform boot? At the time, there were a bunch of related projects, Tramel's SpySpy project, for instance, and the NIST, what is it called, Platform Resilience? That paper, that were all, and then you had the Lattice Mac Exo 3D chip and a few others that said, okay, instead of having an x86 and a TPM, which is basically two computers, separate ROMs and RAMs, and they share a reset line, then we rely on the core root of trust for measurement is in the SPI flash. What happens if we, maybe we should sit on that bus, on the SPI flash bus as well, and that's also where our thoughts were at the time, and we just wanted to see, what can we make? And I think another important aspect here is that an important part of creativity is having hope that you can actually produce something. And I had a thought that how hard is it to make hardware? Is it really that hard? Is it how expensive is it? And so Joachim helped me understand much better the potential of FPGAs and how expensive, or rather not expensive, it is. It's not like it's getting more expensive to do tape outs. It's getting cheaper and cheaper. I think it would be really cool if some of you took a look at the FPGA design and the QEMU emulator, and then thought about, if I don't have to buy my SoC from ARM or Intel, what do I want the handoff between hardware and firmware to look like? If I key derivation function there, for instance, what do I want on which side of the hardware boundary, so to speak?
Thank you. Appreciate it.
All right. Thank you very much. Last question. But they will find you also after the lunch break, basically,
right,
in the exhibition
Thank
room.
you, guys.
But last question.
Yeah, really cool hardware, basically an open source FPGA playground. I have two small questions. One is, why are you decided to use USB to UART converter? Was it impossible to synthesize, so connect ICE directly to USB-C?
Well, that's actually the issue. The ICE40 FPGA that we have is it's the biggest ICE40 Ultra Plus that you can get, and getting a USB core in there is basically eating up like 50-60% of the FPGA.
Yeah,
we're at like 84% fill rate right now, so it's going to be, so if we could get a bigger FPGA that we can use open source tool for, then we're definitely going to do that as a next step. Right?
Yeah, got it. Then the second question would be, one of the most interesting application for this kind of hardware as a playground would be to use USB-C port as a DMA capable interface, so we can run PCI Lich on it. And yeah, you already answered that. The piece itself is not capable enough.
Yeah. True.
All right. Thank you very much. Oh, sorry. Anything else? Okay. You will find all of you, right, in the next room after the lunch break. We will have another talk coming up. So very tiny break, 1-2 minutes. Thanks again.
All right. Thank you.